It is acceptable to tap a 480 volt, three-phase circuit to feed a 3 kilovolt-ampere transformer to obtain 120 volt single-phase power for a control pile. The transformer primary should be connected to two phases of the 480 volt supply, specifically phases A and C in this scenario. The transformer secondary will then provide the desired 120 volt single-phase output. This practice is common in industrial and commercial electrical systems when a lower voltage is needed for control circuits or other auxiliary equipment. Overcurrent protection is crucial for the secondary side of the transformer. Adequate overcurrent protection for the secondary of the transformer is paramount to protect against overloads and short circuits. The size of the overcurrent protection device, such as a circuit breaker or fuses, must be carefully selected based on the transformer's secondary current rating and applicable electrical codes, such as the National Electrical Code. Firstly, determine the full load secondary current of the 3 kilovolt-ampere transformer. The formula to calculate this is kilovolt-amperes times 1000 divided by the voltage. In this case, 3 kilovolt-amperes times 1000 is 3000 divided by 120 volts, which equals 25 amps. Secondly, refer to NEC section 450.3 to determine the allowable overcurrent protection for the transformer. This section provides guidance on the maximum size of the overcurrent device based on the transformer's rated primary and secondary currents. Thirdly, the overcurrent protection device should be sized no greater than 125% of the transformer's rated secondary current if the primary overcurrent protection is set to the lower values allowed in NEC section 450.3. In this case, 125% of 25 amps is 31.25 amps. Therefore, a 30 amp circuit breaker or fuses would be suitable for the secondary protection. Fourthly, consider using fuses or a circuit breaker with an interrupting rating sufficient for the available fault current at the transformer's secondary terminals. This is essential to ensure that the overcurrent device can safely clear a fault. Fifthly, install the overcurrent protection device in a readily accessible location near the transformer's secondary terminals. This allows for easy access for maintenance, inspection, and resetting the device if it trips. Sixthly, ensure that the transformer is properly grounded according to NEC Article 250. Grounding helps to minimize the risk of electric shock and provides a path for fault current to flow back to the source, causing the overcurrent device to trip. Seventhly, label the transformer and the overcurrent protection device with clear and concise information about the transformer's voltage, kilovolt-ampere rating, and the size of the overcurrent protection device. This helps to prevent confusion and ensures that qualified personnel can easily identify the equipment. Eighthly, verify that the installation complies with all applicable local and national electrical codes. This includes checking for proper wiring methods, conduit fill, and clearances. Ninthly, perform a thorough inspection and testing of the transformer and the overcurrent protection device before energizing the circuit. This helps to identify any potential problems and ensures that the equipment is operating safely and correctly. Tenthly, maintain accurate records of the installation, including the transformer specifications, the size of the overcurrent protection device, and the date of installation. These records can be useful for future maintenance and troubleshooting. The primary conductors supplying the transformer should also be properly sized and protected. Refer to NEC Table 310.16 to determine the appropriate conductor size based on the ampacity of the circuit and the type of insulation. The conductors must be protected by an overcurrent device at the source of the supply, which in this case is the 480 volt, 3-phase panel. The size of this overcurrent device should be based on the ampacity of the conductors and the transformer's primary current rating. To calculate the transformer's primary current, use the formula kilovolt-amperes times 1000 divided by the voltage. In this case, 3 kilovolt-amperes times 1000 is 3000 divided by 480 volts, which equals 6.25 amps. The primary conductors should be sized to carry at least 125% of the transformer's primary current, which in this case is 7,8125 amps. Therefore, a minimum of 14 American wire gauge copper conductors would be suitable, assuming the conductors are rated for 75 degrees Celsius. The overcurrent protection device at the 480-volt panel should be sized no greater than 250% of the transformer's primary current, according to NEC section 450.3. In this case, 250% of 6.25 amps is 15.625 amps. Therefore, a 15-amp circuit breaker or fuses would be suitable for the primary protection. The conductors should be installed in conduit or other approved raceway to protect them from physical damage. The raceway should be properly supported and secured. All connections should be made using approved connectors and terminals. The connection should be tight and secure. The transformer should be mounted in a location that is accessible for maintenance and inspection. The location should also be well ventilated to prevent overheating. The transformer should be protected from moisture and other environmental factors. A disconnect switch should be installed near the transformer to allow for easy isolation of the transformer from the power supply. The disconnect switch should be properly labeled. All work should be performed by qualified personnel in accordance with all applicable codes and standards. Safety precautions should be taken to prevent electrical shock and other hazards. Before working on any electrical equipment, always de-energize the circuit and verify that it is energized with a voltmeter. Wear appropriate personal protective equipment such as safety glasses, gloves, and insulated tools. Be aware of the potential hazards of working with electricity and take steps to mitigate those hazards. By following these guidelines, you can safely and effectively tap a 480-volt three-phase circuit to feed a 3 kilovolt-ampere transformer for 120-volt single-phase power. The installation should be inspected by a qualified electrical inspector to ensure that it complies with all applicable codes and standards. Regular maintenance and inspection of the transformer and the overcurrent protection devices will help to ensure the continued safe and reliable operation of the equipment. When tapping the 480-volt circuit, ensure that the voltage between phases A and C is indeed 480 volts. Use a voltmeter to verify this before connecting the transformer. If the voltage is significantly different, there may be a problem with the supply voltage or the transformer may not be compatible with the voltage. Also, confirm that the transformer is designed for connection to a 480-volt two-phase supply. Some transformers may be designed for connection to a 480-volt three-phase supply using a delta Y configuration. Connecting a transformer designed for a three-phase supply to a two-phase supply may damage the transformer. The transformer should be mounted on a solid, level surface. This will help to prevent the transformer from vibrating or shifting, which could damage the transformer or the connections. The transformer should be protected from physical damage. If the transformer is located in an area where it could be struck by vehicles or other equipment, it should be protected by bollards or other barriers. The transformer should be protected from exposure to corrosive substances. If the transformer is located in an area where it could be exposed to corrosive substances, it should be coated with a protective coating. The transformer should be inspected regularly for signs of damage or wear. If any damage or wear is found, the transformer should be repaired or replaced. The transformer should be cleaned regularly to remove dust and dirt. Dust and dirt can accumulate on the transformer and reduce its cooling capacity. The transformer should be tested periodically to ensure that it is operating properly. The test should be performed by a qualified electrician. The results of the test should be recorded and kept on file. If the transformer is no longer needed, it should be disposed of properly. Transformers contain materials that can be harmful to the environment. The transformer should be disposed of in accordance with all applicable regulations. When selecting a transformer, it is important to consider the load that it will be supplying. The transformer should be sized to handle the load without overheating. The transformer should also be selected based on the voltage and frequency of the supply and the load. The transformer should be energy efficient. An energy efficient transformer will save money on electricity costs. The transformer should be reliable. A reliable transformer will provide years of trouble-free service. The transformer should be easy to install and maintain. An easy-to-install and maintain transformer will save time and money. The transformer should be backed by a warranty. A warranty will protect you in case of defects. When installing a transformer, it is important to follow the manufacturer's instructions. The instructions will provide information on how to install the transformer safely and correctly. The transformer should be installed in a location that is accessible for maintenance and inspection. The location should also be well ventilated to prevent overheating. The transformer should be protected from moisture and other environmental factors. The transformer should be grounded properly. Grounding helps to prevent electric shock and damage to equipment. The transformer should be tested after installation to ensure that it is operating properly. The test should be performed by a qualified electrician. The results of the test should be recorded and kept on file. When maintaining a transformer, it is important to inspect it regularly for signs of damage or wear. If any damage or wear is found, the transformer should be repaired or replaced. The transformer should be cleaned regularly to remove dust and dirt. Dust and dirt can accumulate on the transformer and reduce its cooling capacity. The transformer should be tested periodically to ensure that it is operating properly. The test should be performed by a qualified electrician. The results of the tests should be recorded and kept on file. If the transformer is no longer needed, it should be disposed of properly. Transformers contain materials that can be harmful to the environment. The transformer should be disposed of in accordance with all applicable regulations. In addition to the 3 kilovolt-ampere transformer for the 120-volt supply, ensure that the 480-volt three-phase circuit is also adequately protected with an appropriate overcurrent device. The size of this overcurrent device should be based on the ampacity of the conductors and the load that it is serving, including the 3 kilovolt-ampere transformer. It is important to consider the voltage drop in the conductors, especially over long distances. Voltage drop can cause equipment to malfunction or operate inefficiently. The voltage drop can be calculated using the following formula: voltage drop equals 2 times K times A times D divided by circular mils, where K is the constant depending on the conductor material. For copper, the constant is 12.9. I is the current in amps. D is the distance in feet, and circular mils is the area of the conductor in circular mils. The voltage drop should not exceed 3% for power circuits or 5% for lighting circuits. If the voltage drop is too high, the conductor size should be increased. Ensure that all wiring is done in accordance with the National Electrical Code and any applicable local codes. The NEC provides detailed requirements for wiring methods, conductor sizing, overcurrent protection, and grounding. Adhering to these requirements is essential for ensuring the safety and reliability of the electrical system. Consult with a qualified electrician if you have any questions or concerns about the installation. A qualified electrician can provide expert advice and ensure that the installation is done correctly. Remember to always prioritize safety when working with electricity. Electricity can be dangerous, and it is important to take precautions to avoid electric shock and other hazards. Always energize the circuit before working on it, and use appropriate personal protective equipment. The integrity of the grounding system is also critical. A properly installed and maintained grounding system provides a low impedance path for fault current to flow back to the source, causing the overcurrent device to trip and energize the circuit. This helps to protect people and equipment from electrical shock and damage. Inspect the grounding system regularly to ensure that all connections are tight and free of corrosion. Test the grounding system periodically to verify that it is functioning properly. If any problems are found, they should be corrected immediately. Finally, always remember to document the installation thoroughly. Keep accurate records of the wiring, conductor sizes, overcurrent protection devices, grounding system, and any other relevant information. This documentation can be invaluable for future maintenance, troubleshooting, and modifications to the electrical system. In summary, tapping a 480-volt, three-phase circuit to feed a 3 kilovolt-ampere transformer for 120-volt single-phase power is a common and acceptable practice, provided that all applicable codes and standards are followed. Proper overcurrent protection, conductor sizing, grounding, and voltage drop considerations are essential for ensuring the safety and reliability of the installation. Consult with a qualified electrician if you have any questions or concerns. Always prioritize safety when working with electricity. Always use appropriate lockout-tagout procedures when you are de-energizing a circuit. This will ensure that the circuit remains de-energized while you are working on it. A lockout-tagout procedure involves placing a lock and a tag on the circuit breaker or disconnect switch that controls the circuit. The lock prevents the circuit breaker or disconnect switch from being turned on, and the tag provides information about why the circuit is de-energized and who is working on it. Only the person who placed the lock and tag on the circuit breaker or disconnect switch should remove them. This will ensure that the circuit is not energized until the work is completed and it is safe to do so. Before energizing the circuit, inspect the work area to ensure that all tools, equipment, and debris have been removed. Also, verify that all connections are tight and secure. Once you are satisfied that the work area is safe, you can energize the circuit. After energizing the circuit, monitor it closely for any signs of problems. If you notice any problems, de-energize the circuit immediately and investigate the cause. In addition to the above considerations, it is also important to consider the ambient temperature in the area where the transformer is located. The ambient temperature can affect the transformer's ability to dissipate heat, which can lead to overheating and failure. If the transformer is located in a hot environment, it may be necessary to derate the transformer's kilovolt-ampere rating. Derating involves reducing the transformer's kilovolt-ampere rating to compensate for the higher ambient temperature. The amount of derating will depend on the transformer's design and the ambient temperature. Consult with the transformer manufacturer for guidance on derating transformers in hot environments. Also, consider the altitude of the location where the transformer is installed. Altitude can affect the transformer's insulation strength. At higher altitudes, the air is thinner, which can reduce the dielectric strength of the insulation. If the transformer is installed at a high altitude, it may be necessary to use a transformer with a higher insulation rating. Consult with the transformer manufacturer for guidance on selecting transformers for high-altitude applications. When selecting conductors for the 480-volt circuit, consider the type of load that the circuit will be serving. If the circuit will be serving a continuous load, such as a motor, the conductors must be sized to carry at least 125% of the motor's full load current. This is to account for the fact that motors can draw more current during starting. If the circuit will be serving a non-continuous load, such as lighting, the conductors can be sized to carry the actual load current. Also, consider the derating factors for the conductors. Derating factors are used to reduce the ampacity of conductors to account for factors such as ambient temperature, conduit fill, and bundling. The derating factors for conductors are specified in the National Electrical Code. When installing conductors in conduit, be sure to use the correct size conduit for the number and size of conductors. The National Electrical Code specifies the maximum number of conductors that can be installed in a given size conduit. Overfilling conduit can damage the conductors and reduce their ampacity. When making connections to the transformer, be sure to use the correct type of connectors for the conductors and the transformer terminals. Use connectors that are listed and labeled for the intended application. Make sure that all connections are tight and secure. Loose connections can cause overheating and arcing. When grounding the transformer, be sure to use the correct size grounding conductor. The National Electrical Code specifies the minimum size grounding conductor for different size transformers. The grounding conductor should be connected to a grounding electrode system, such as a ground rod or a metal water pipe. The grounding electrode system should be installed in accordance with the National Electrical Code. When testing the transformer after installation, be sure to use a qualified electrician. The electrician will use a variety of test equipment to verify that the transformer is operating properly. The tests will include checking the voltage, current, and insulation resistance. The electrician will also inspect the transformer for any signs of damage or wear. If any problems are found, they should be corrected immediately.